Physics Notes, Unit 23, Part B, Faraday's Law, generating electricity by moving a magnet or changing the magnetic field by a coil of wire or moving the coil of wire, which is the more efficient way of doing it. Just one note, here's our equation for Faraday's Law once again, which we will be applying here. I haven't mentioned this recently, but we pretty much ignore the negative. The negative is just a matter of which way the current flows. And I did some examples with Lenz's law. That's going to be a minor issue in these problems. In fact, when we do the calculations, it's not an issue at all. I ignore the negative. The big thing is what's changing here. Now, in this problem, this is a famous problem. There's an example problem like this in the book in chapter 23. You have a couple of metal rails with maybe a wire that connects across these two metal rails with maybe a resistor or a light bulb. And then you're going to pull this green arrow represents somebody pulling this conductor. It's probably just a metal wire that's connected or touching the metal rails. It's being pulled to the right. So you have a loop here. It's a square or rectangular loop. It's a circuit. And then in this case, you have magnetic field towards the floor. It could be towards the ceiling. But what's important here is what's inside this loop. And just to kind of review Lenz's law real fast, like which way the current's flowing. It's showing you that the current's going to flow counterclockwise here when you do this, but let me explain why the current's going to go counterclockwise. They could ask you, which way will the current flow if you pull this rod to the right? So let me just go one more example of Lenz's law. This one's a little bit easier as far as looking at the visual here, I think. Because what happens here is, if you pull this rod to the right, you're increasing the amount of flux. Each of these little X's basically represent flux, magnetic flow towards the floor through this loop, this rectangular area that's enclosed, all right? And you're increasing the flux, okay? You're increasing the flux that's from some kind of external source. So all that flux you see there with those X's, that's from some kind of external magnet. So what happens is the current's going to flow in this loop to try to counter that flux. So now it's going to try to create its own flux, its own magnetic field in that center part of the loop to counter that. And by our own conventions, if you take the right-hand rule, I'm going to look at this wire up here, it's right-hand rule number 2. Going back to the unit, I believe, 22, when you have a current flowing in a wire, the magnetic field around the wire, this is totally different than the ones that are already there. I'm going to draw this. So around a wire, well, actually, I'm going to go back over here and draw it, and I'll erase it. If I have a wire with current going this way, this is how we draw the magnetic field. The tangential lines, these are the tangential lines to circles as the magnetic field circles around that wire. So that would be the magnetic field due to the current in the wire, not due to the magnetic field that's already there. So in fact, if you go to this current right here flowing to the left, the magnetic field that the wire creates, I don't really care about this stuff up here. That's all in addition to the field that's already there. But it's going to have magnetic flux that's tangentially towards the ceiling as that magnetic field circles around the wire. And that's why the current is towards the left here, because if you look at those last 3 circles I drew, the ones with the dots in it, okay, those are towards the ceiling. And what those do is they're trying to reduce the amount of flux that's in that rectangular loop. It started with those 9 X's, okay? I have an X here, 1, 2, 3, 4, 5, 6, 7, 8, 9. And maybe I should just use a different color because those are all from an external source. I'm going to make them blue. That's the magnetic field from an external source. But when the current flows, it creates its own magnetic field to try to counter the fact, to kind of keep it at 9 instead of increasing to 12. So I went from 9 blue flux lines, and those are just a uniform magnetic field that's straight towards the floor. Not due to any currents as far as we know. It's just some kind of big magnet it has a uniform magnetic field. It's not even circular, it's linear, towards the floor. But the wire's magnetic field is represented in red. It's going to try to then, what you look at is inside this rectangle. You don't care what's outside the rectangle. I can erase the other side. I don't care about these right now. I don't care about the ones that are on the outside of that wire. The tangents are going to be towards the ceiling, and those then will counteract the increased blue flux. That's more blue flux towards the floor. Upward flux towards the ceiling cancels that out to a degree, and that's called it's Lenz's law. That's trying to oppose the change that caused it. All right, so it's an opposition. Anyways, that's why the current flows counterclockwise in this loop, as already indicated. That's another review of Lenz's law. So I'm going to erase all that. That's Lenz's law. But now we're going to connect what's called motional EMF to the Hall effect equation, which we really had back. We had this back, I think, in Unit 22. Motional EMF. So we're going to get back kind of a proof of the Hall effect equation, which is used as a magnetic field detector, or for flows of fluids through pipes and possibly through arteries. I did that example in Unit 22. Okay, but bottom line, okay, is as you pull this wire to the right, if you pull this wire to the right, it's increasing the area. Now, a couple of equations that are here that are important. This equation, I'm going to circle it in red over here. We have V, the velocity with which you pull that wire to the left, or to the right. Basically, your average velocity, it's going to be a constant velocity here, is your distance over your time. So they're going to pull it a distance of delta x in a time of delta t. In other words, they're showing you the delta x. So basically, velocity is the distance you go in a time that it takes you to pull that distance. You're going to pull that distance in that time, so that's just basically a definition way back. I think it's like the second thing we had in Physics 201. It's the definition of average velocity. Distance or displacement over time. This could be speed here. It doesn't matter. You're going in a straight line. Delta x over delta t. Now, here's the thing. If you take that equation, that means that delta x equals v times delta t, or just v times t. So I'm just rearranging that equation. All right, that's important. I'm going to use that in a second here. Now, that area, which is shaded, they have it up here at the top. I'll circle it up at the top. That's the increase in area. That's going to be part of Faraday's law. All right, to figure out the increase in area, excuse me, the increase in area is just the length times the width. So the delta x is the width, and the length of this is the length of this wire. Okay, I'm going to call the length of the wire L. That's how they're calling it little l. I'm going to call it capital. Way over here to the right. Over here. I'm calling that's the length of the wire that's being slid to the right. And it's being slid a distance of delta x to the right. So that area that's shaded, I'll just highlight it right there. That's the increase in area. That's the new area. I'm just putting hash marks in there. All right. So the area is just the delta x, okay, or length, the length times delta x. I'm going to say delta x times L. It doesn't really matter. L times delta x or delta x times L. All right. That's the area. You multiply the width of a rectangle times the height of a rectangle. Doesn't matter what order you put it in. They have L times delta x. Same thing. Okay, so that's now. So what's going to happen here is I'm going to take, I'll do blue. All right, I'm going to take this and plug it in for delta x. So what you end up with is the change in area here. The change in area is going to be V delta t times L. V delta t times L. Now, I'm going to take that delta area, that's the change in area, that's the increase in area, it's V delta t times L, and put it in for A. Basically, it's delta A. I'm putting the delta with the A. That delta in the delta equation for the change, what's happening here is whatever's changing. The number of loops, that doesn't change. The amount of magnetism in that area is changing. That's my delta right there. V delta TL, it causes the increase in flux. So now I plug in there. I get E equals, I'm going to get rid of the negative, and now I'm plugging into delta. I'm going to have B, and then it's going to be V delta T times L. Over delta T. All right, the delta T's will cancel. The delta T's cancel. So then you end up with, basically, BVL, which I don't like it that way. I mean, that's where V is the velocity. The way I've written it, the Hall effect equation, is it's the same equation, BLV, so I'm kind of switching these around. Doesn't matter what order you multiply them in, but that's the Hall effect equation. In this application, they call it motional EMF because something's moved, the wire is moving in a straight line or being pulled to the right. Okay, so problem 4 then has some information. I got to go back up to the top here. So it says if the length of that wire, the sliding rod, is 15 centimeters, moving at 5.5 meters per second, and it gives you the strength of the magnetic field. No, find the strength of the magnetic field density, if you have 150 volt potential difference, 150 volt EMF. So I'm just going to plug into the Hall effect equation over here, E equals BLV. That equation that we've had before, I just proved it. It tells you that E, this is a straight substitution. 150, we're looking for B, will be in Teslas. L is 0.15 meters, and the velocity is 5.5 meters per second. So that's just divide the 150 by 0.15, and then divide by 5.5, you get 180 Teslas. That's quite a strong magnetic field because it's a lot of potential difference, 150 volts. Okay, next example. You have a non-ferrous screwdriver. In other words, it's not iron or nickel, a non-magnetic screwdriver. It could be aluminum. The shaft of the screwdriver is aluminum. It's another one of these. It's pretty much straight substitution. We have the EMF equals BLV, and so we're looking for the EMF. It tells you the B, so this is pretty easy. Times the length of the screwdriver as it cuts through the magnetic field. We're assuming it's perpendicular. It tells you it's perpendicular. Once again, all these problems for now, we get the maximum effect. We're using a perpendicular orientation. For all of these, you would get less effect if you don't have it perpendicular. And it says what's the length is 0.13 meters, and the velocity is 7.00. So that's just a straight, plug those in, 1.8 volts. 1.8 volts. Once again, it's a pretty strong magnetic field. 1.8 volts is not a whole lot, but you could generate some current if you picked up a circuit, but you wouldn't be hooking that up to a circuit. It's a screwdriver. Well, here's an interesting one. This is basically from the book. It's some kind of theoretical situation where you have like a space shuttle. There's a diagram here. I took this right out of the book. With a really long wire. It says it's 18 kilometers long. 18 kilometers. That's probably going to be, I don't know, 10 or 12 miles long conductor. And you're moving it very fast because 7.80 kilometers per second. This is a space shuttle in orbit in outer space. The Earth's magnetic field goes out into outer space. So in this particular diagram, all these X's represent the Earth's magnetic field at a location where the shuttle is attached to some kind of satellite, and it's pulling that wire across that magnetic field. It's basically an application of the motional EMF. So once again, we're going to substitute in E equals BLV. All right, so once again, we proved that from Faraday's law, delta NBA over T. So those are the two equations we can use to figure out how much voltage is induced as you move a magnet or a wire in a magnetic field. So this one starts off again, pretty much substitute in. We're going to get the motional EMF, so we're going to do part A. The motional EMF is, okay, the Earth's magnetic field. This is a pretty reasonable estimate of the Earth's magnetic field. It fluctuates a little bit, but 5.0 times 10 to the negative fifth Teslas. And we're going to assume it's uniform and perpendicular to our wire. The length of this wire is 18 kilometers. That's 18,000 meters. That's 18,000. And times the velocity. That's 7,800. 7,800. So 7.8 kilometers. Once again, kilo is 3 zeros or 3 decimal places. So the 18 kilometers turns into 18,000 meters, and the 7.8 kilometers turns into 7,800 meters per second. All right. So that's just pretty much a substitution. Well, it is not pretty much a substitution. It's a substitution. That comes out to be about 7,000 volts. That's a lot of voltage. Okay. Now, it says, though, if the current of 9.5 amps, which is a lot of current, what magnetic force, drag force, does this produce? Well, part B here, going back another unit, is F equals ILB. The magnetic force on a wire, when it is pulled through or has current in a magnetic field. Okay, so as it's being pulled through, there's a potential difference. The current will flow, and when there's current flowing in the wire, as the current flows in the wire, then there's going to be a force, and it's a drag force. Okay, and we'll apply our right-hand rule number 1 here in a few minutes, but just going to plug in here. We're going to look for the drag force. F equals, I probably should give myself more room. Looking for I. It says the current is 9.5 amps. The length of the wire, once again, is 18,000. That's 18,000. Let's squeeze it in. And B is the 5 times 10 to the negative fifth. Hopefully you can, so it's 5, that's going to go off the page, times 10 to the negative fifth. So that's times 10 to the negative fifth there. You won't see it off the page, but you plug those all in. 9.5 times 18,000 times 5 times 10 to the negative fifth. If you multiply all those numbers, you get 8.6 newtons of drag, which is not a whole lot. It's because the magnetic field is not that strong. But that's the drag. If I go back a little bit here, you could have done the same thing up here, because when you pull this wire to the right, it requires a force. There's going to be some resistance because it doesn't want to go there, because you can't just get free voltage and free current, because it takes some energy or some force to pull it, because there's going to be, like, once again, a drag force like we just calculated that. You could figure that out in this problem as well. F equals ILB. What kind of force is going to try to be slowing down the wire that you have to then exert to keep the wire going? Or in other words, if we go back to this diagram, if we do the right-hand rule, all right, number 1, forget about the green vector right now. So if you use the right-hand rule in this diagram, the x-axis, like if this is on your tabletop, your x-axis is toward the floor. That's the magnetic field. That's the way your fingers have to point towards. So you point your fingers towards the floor. The current is towards the top of the page here. All right. So your thumb points towards the top of the page, and your palm points to the left. So the drag force will be this way. That's going to be the drag force. That's the magnetic force that we just calculated. It's 8.6 newtons. All right. That's what's trying to slow it down. So you have to have a forward force of that amount to keep it going forward at a constant velocity. All right. So there's a force trying to slow this down. And if you don't have a forward force that equals that, then the thing will slow down over time. So let's investigate that. If we allow that force to slow it down, if there's no counter force to try to keep it going at constant velocity, that's what this problem implies. At part C, how much kinetic energy is removed from the system in 1 hour if we ignore the other effects. So even though this will slow the system down if we don't put energy in. But what would that force, how much energy would that take out? Okay, now, going back a few units, okay, power equals energy or work over time. Or in other words, energy equals power times time. This is from actually several units back. Energy is power times time. Now also, power equals current times voltage, electrically speaking, but it's also force times velocity in mechanical systems, because now we have kind of a mixture of mechanical and electrical systems here. So I'm pulling a bunch of old equations out that you wouldn't think of probably. But I'm going to plug this in for P. So the energy that's used in a given amount of time is going to be the force times the velocity times the time. All right, so I'm going to plug into that. The energy that's dissipated over time is the force that drag exerts, 8.6 newtons of force. The velocity, if we assume the velocity stays constant at 7,800, which it will slow down, but let's say it stays constant. So we're ignoring that it slows down. If we just let this force drag the wire, it'll slow the whole system down. Times the time. Now it's 1 hour. And you can do the conversion, but 1 hour turns out to be 3,600 seconds. 1 hour, you can do the math, is equal to 3,600 seconds. 60 seconds in a minute, 60 minutes in an hour, 60 times 60 is 3,600. So the energy that's going to be lost, if you multiply those three numbers, is 2.4 times 10 to the 8th joules. It sounds like a lot. So, in everyday usage, it's quite a bit here on Earth. A lot of energy lost due to that force, which could slow the system down, which could pull this thing out of orbit if you allow that to continue. Unless you put some energy in and burn some fuel for your space shuttle, it's going to slow it down. The question is, by what percent does that slow it down? That's part C, I think. There's going to be a percent loss. What loss of kinetic energy, and so forth. So what percent loss? Okay. Well, this is going to be the loss of energy due to that drag force. So in part D, though, let's figure out what the initial kinetic energy is. Once again, going back to Physics 201. So the kinetic energy initial of the system is 1/2. It says it's 100,000 kilograms of mass times the 7,800 meters per second squared. Don't forget to square that. I almost did. So the initial kinetic energy of this system is 3.0 times 10 to the 12th joules. That's a lot of kinetic energy. So, but if you drag this cable for an hour, you lose that much energy, which is going to slow you down. We're ignoring the slowdown right now, but the question is, what percent loss is that? Well, if you lose 2.4 times 10 to the 8 joules out of the original 3.0 times 10 to the 12th, you divide that and multiply by 100, and then multiply by 100 to get your percent. Okay, it turns out to be 8 times 10 to the negative third percent. So it's 8, I gave one sig fig there, 8 times 10 to the negative third percent. So 0.008% loss. I can put that in decimal form, 0.008% loss. Okay, the point being this, it's a big number. It looks like it is a big number. It's a lot of energy, but it's a very small percent loss of energy. However, if you let this continue on and on and on, it will eventually slow this system down enough and pull the thing out of orbit, because you've got to maintain your velocity to maintain your orbit. Just kind of a fun little problem applied to a theoretical situation to generate current in the space shuttle example. Yeah, and as far as I know, I don't think they've ever, well, I'm sure they've never tried that situation to generate electricity like that with using a space shuttle. But bottom line is, you don't create a current for free. You can't get free electricity. It takes energy on your part to convert into the electrical energy. Because and it kind of goes along with Lenz's law. When you try to generate electricity, there's an opposing effect. It tries to oppose you. So it takes energy input on your part then to convert from your system, some kind of mechanical, chemical energy into the electrical energy. So sometimes we refer to this opposition to your created voltage, a back EMF. It's trying to stop it. As you try to move the magnet or rotate the coil, by the nature of the induced current and the induced EMF, it's opposite of your EMF, opposite your voltage. So we call that back EMF. Eddy currents are little currents in a conductor. I'm going to show you a video on this. Once again, they're all kind of connected to this back EMF that try to oppose the voltage that's being created, or the loss or gain of magnetic field in your loop. It gives rise to specific things called magnetic damping. I'm going to show you these videos will hopefully explain this. It's a kind of like a drag force, similar to that drag force you had in that wire in that space shuttle example, but we're talking more about in metal conductors. It's actually used in magnetic braking, like even in roller coasters. Or if you've ever been on a giant drop at Six Flags Great America, they use magnetic braking at the very bottom because it's a frictionless system. The only thing is, it can't completely stop you. It stops you the faster you're going, the more effective it is, but the slower you're going, the less effective it is. Okay, because then you're not changing the magnetic field if you're not moving. I'll show you an example in a minute. You can also use this idea to separate magnetic materials. You can use this idea in a metal detector. Maybe you've seen people at beaches with metal detectors. They use little eddy currents, these little currents that are like from a back EMF or induced voltages, to then detect metal objects that are buried, that aren't touching or they're unseen to the visual eye, but can be detected from a distance. You can dig them up and so forth. So let me show you a little video that might help explain these concepts. All right, let me try to step you through a video here, and I may have to fast forward a little bit. So magnetic braking, they have a copper tube. There's a little window right there, and you won't be able to see it too well. They're going to drop a magnet through this copper tube, which is a non-ferromagnetic material. Magnets don't stick to it, but when you drop a magnet through there, it goes kind of slow. There's magnetic braking. Maybe you saw it moving slowly through that tube. It went through this view window there. If I go back a little bit, you can maybe see it. I'll try it again. Hopefully I'll capture that. So watch the magnet come through. It's going to come through right there, and it falls out the bottom. But it goes slowly through that tube. There's magnetic braking because it creates eddy currents, which I'll explain here in the video as we go forward. So let me try to fast forward this a little bit. Well, they're going to change the speed. Okay, so they're going to show you a top view. Like that's looking down into the tube. And when you drop the magnet, it doesn't fall like in free fall. There's a resistive back EMF because of eddy currents, which they'll explain with a diagram. Now that's slow motion though. The first one wasn't slow motion. The magnet's not rubbing on the sides, and it's not attracted to the copper. So this shows you how there's the magnet going slowly through that tube. Now it's showing you the magnetic field of the magnet. The magnetic field lines of the magnet as it falls through. As that magnetic field of the magnet falls through that copper tube, because of Faraday's law and Lenz's law, little currents are set up that oppose that magnetic field flowing through that copper tube. So now these are showing the little eddy currents, small localized currents in the copper conductor. And copper works really nice because it's a good conductor of electricity, and you get these magnetic fields that then oppose the magnetics. The magnet that's falling through there opposes that magnet's magnetic field, so it keeps the magnet from going faster. The faster the magnet tries to go, the more effective this braking action is. The slower the magnet goes, but the weaker it would be. But it reaches an equilibrium very quickly as the magnet falls through that tube, and it just goes with a constant velocity. It's not accelerating. So that's kind of a fun demonstration of eddy currents. And here's another example of magnetic braking, like you would have possibly on a roller coaster ride at an amusement park. They're going to show you a copper conductor or any metal conductor, and it's best if it's a non-magnetic material. But what they have in this situation is they have two solenoids here that have no current running through them right now. Solenoids are a bunch of wrapped coils of wire, as we've talked about before. But there's a switch over here. This big handle is going to put some current in those solenoids. They're pretty big solenoids. And once those solenoids have current in them, there'll be a magnetic field in this gap between them. There's an air gap between those two big coils of wire. And there's a pendulum here that he's going to swing back and forth. This pendulum with a red bottom is going to be like a swinging back and forth, but it's not rubbing on anything like friction. It's just going to be swinging through the air. Let me start this up here. And there it shows you the copper pendulum. Then he's going to take it off and start swinging it. He's going to swing it first without the magnetic field turned on. That was the DC power source over here. And then he's going to flip the switch to turn the magnetic field on, to turn the current on. Once the current goes on in these coils, there'll be a magnetic field that creates eddy currents. So no magnetic field right now because the current is not on. There you go. Okay, so I backed this up one more time just to show you this. It happens so fast. Here's the DC power source that turns on current that then would activate a magnetic field between these two solenoids. There's your solid conductor again. It's going to swing first without a magnetic damping. Then he's going to flip the switch. Let me pause it for a second. Okay, so it was swinging freely. There was no current in these coils, and there's no magnetic damping. Once he flips the switch, which he's going to do here real quick once I turn this on, current flows in the coils, magnetic field is created around the coils, and then the magnetic fields will create eddy currents in that solid copper conductor, which will then create basically a resistive force, magnetic braking without anything touching or rubbing with physical friction. So here we go. I'm going to turn this on. And the magnetic damping stops the swing. All right, so those are some practical applications of Faraday's law, in addition to the main application of Faraday's law, is the generation of electricity, which is the ultimate importance. Is, how do we make electricity? Moving a magnet by a magnetic field. But then all these subtopics, basically we can also use this to make metal detectors and do magnetic braking. But the main application of Faraday's law is generating a voltage by moving a coil of wire, rotating a coil of wire in a magnetic field to produce electricity in the first place. All right, there's one more major topic in this unit, and that is transformers. So stay tuned for that. We're not talking about transforming a car into a person like the Transformers movies, but we're talking about transforming voltages from one type to another type, or one magnitude to another magnitude.